excellent talk, Gerald, and many others. Thank you so much, Ovidiu.
Yeah, so I'd like to thank the organizer very much for inviting me to this incredible place. And it's great to see so many of my friends here. It's really a pleasure. So I'm going to talk about some results that we have with Gerald, who's here, with Sergey is not here, his former student, and he will be, yeah, here, and his former student, Angus. Uh, so one of the topics of the talk will be indeed crossing natural boundaries for Q-series. Not any natural boundaries, I mean, they're not meant to be crossed arbitrarily, but in Q-series we have enough structure for that. And a good number of other aspects about Q-series and their identities that are revealed by resurgent analysis. So that's the synopsis. And all of this and more is in this paper, which is now on archive. It's a pretty long paper, and I extracted some of the things that are most relevant to this workshop. Yeah, since I'm speaking of Q-series, let me start with some notations, and I apologize to those of you who are experts, probably even much more so than I am in Q-series, about the typical notations used in this field. So Q is seen when we are working in the hyperbolic plane with the SL2Z would be e to the pi I tau. And David tells me that the key word to make the distinction between e to the pi I tau and 2 pi I tau is to speak of the elliptic norm function. Okay, so we're in the elliptic norm function. But since one of the purposes is to understand the asymptotic behavior and the analyticity properties of this series, is natural to go to the Roy half plane, and then the notation that goes back at least to Watson is to go to e to the minus alpha if alpha is some parameter of his choice. So there is a variable q, there is a variable q tilde, which comes from q by one of the generators of SL2Z, tau into tau plus 1, which at the level of this variable q means q goes into e to the minus pi square over alpha. Okay, just notations. This is the q Pochhammer symbol. Q tilde is also sometimes denoted by q1, and whenever one wants to see what's on the other side of the boundary, qv is one of the common notations, but also there may be many more. So qv will be 1 over q. Okay, so if you have, so you want to have something concrete in mind, the prototype of a Q series is the Mach theta function f, whose expression is here, is essentially a lacunary series divided by Q Pochhammer, discovered alongside a long list of similar ones by none other than Ramanujan. This is of order 3, and there are Mach thetas of higher order. The classification is not completely sort of maybe systematized, but so Mach thetas go to some high order in any case. What I want to mention is that if you read Ramanujan's description of these Mach thetas and Watson's sort of take on his view of this Q series, the language and maybe the philosophy too, they're amazingly reminiscent of a resurgent approach. I mean, he seemed to be looking for the trans-series representations of these things. I mean, it's amazing, but it's not surprising that it's amazing for Ramanujan. Watson discovers a few more Mach thetas, and at order 3, a very important one is the omega function, whose expression as a Q series is given here. And he relates them to more del-type integrals, which are integrals of this type. They are almost Laplace transforms, and in fact, they are Laplace transforms up to a trivial change of coordinates of, importantly, a trigonometric or hyperbolic trigonometric kernel. Okay, and he finds these sort of important relations between the Q series and the associated Mordell type integrals. That's what's on. And we can think morally that what he did is a form of very clever Poisson summation too, and Euler-Maclaurin summation combined in one. Okay, so these are some typical relations for order 3. This is order 5. A whole lot more of these relations. You have these integrals that are Mordell integrals, and you have these objects that are Q series and Q1 or Q tilde series on the right, and you have all these identities. So these are the examples. This is Mach 10, there is Mach 7, there is Mach 8, and so on. And these are the Mordell type integrals. So that's just to set, the scene for these functions. Okay. Yeah, what is very interesting, you'll see in a moment, is that forget about all the others, take J for the sufficient. So the way you characterize the others is a sort of a matter of how you want to label the orbit of SL2Z. So the others come from, you'll see in a moment. All the others are generated by one of them, or by a Q series, or by any combination. Okay. All right, so I'll keep these notations for a while with me. So there are a number of things that I extracted for this talk, and here are some of them. So we find that Mach theta functions and the Ramanujan-Watson identities arise merely, if I want to say merely, as trans-series representations of the underlying resurgent functions, which are the Mordell integrals. So if you take the Mordell integral and you do a proper trans-series decomposition, you get the Q series and you get the identities, constants, and all. And some new things that are revealed by resurgence analysis. Resurgence analysis provides unique continuation through the natural boundary Q equals 1. Quickly, most of you know that these Q series have the unit. Obviously, these are convergent inside the unit disk. They look like lacunary series. They are not quite lacunary series. Morally, they are. If they were, then the unit circle would be obviously a natural boundary, but it is a natural boundary regardless of this denominator, which is tame. Okay, so what I'm saying here is that resurgent analysis provides you with a way to go from the interior of the circle or the disk or the circle to the exterior, or in terms of half planes, from the upper half plane to the lower half plane. Yeah. Yes. I mean, at the level of integrals, if I understand well the question, there is absolutely no problem to do a continuation through what is called the natural boundary, because they don't. They're analytic through, the real line or through the circle. And maybe I didn't understand the question well. In order for this machinery to work, you need a special type of kernels of those integrals, and that special type is essentially a trigonometric or hyperbolic trigonometric function. So you need some form of meromorphicity. Actually, what you need is some compatibility with SL2Z or SL2 to Z in order to apply a sufficient number of transformations to have the rich kind of information to go from one side to the other. So the method of continuation is one of unique continuation. To have unique continuation, you have to have a set of properties that need to be preserved by continuation, and then a uniqueness theorem. So whether this is limited to the trig class, this we don't know really. So we have this unique continuation. The unique continuation is crucial to something that is quite surprising in some ways, that this continuation reveals the origin of the identities among these various types of mock thetas. So the identities of Watson generalized to mocks 5 and 7 and 10 and whatnot. They all come as trans-series representation on the other side. Why on the other side, we'll see in a moment. Okay, it indicates, and then we proved, that you have a uniqueness of a Q-series decomposition of a Mordell integral, both on what we call the easy side, the trans-series side, which is beyond the boundary for Q greater than 1, and also on the more difficult side, which is the mock theta side. And this whole machinery of resurgence gives procedures to get Q-series coefficients numerically. So this was observed by Gerald, and this is what triggered the much more thorough resurgent analysis of the problem. So if you wish, this is the origin of this whole analysis. And getting the coefficients numerically, what do I mean by that? So you have the Mordell integral, suppose you have no formula in terms of those lacunary / Pochhammer, Q-Pochhammer things. You can get the coefficients numerically. So Gerald got 20 coefficients out of a new kind of class of, if we want to call them mock thetas. Okay, so it's useful per se. It's useful to get this kind of information when you don't have formulas and in other cases. And the essential mechanisms at play are resurgence and this robustness. In fact, it's permanence. And if I speak of that, I'm speaking by analogy with permanence of relations in analytic continuation. So a similar permanence of relations applies to resurgent functions. One ingredient, the other ingredient is some form of modular transformations that we need. Okay, so if I spoke of preservation of relations, I'm going to talk first about that, as Borel summation is an isomorphism, between functions and formal representations, the formal representations being trans-series. This is generalized Borel summation. Okay, so let me start with Borel summation. There are two ingredients in Borel summation. One is the duality Laplace inverse Laplace. You take an inverse Laplace transform of a formal series. So what is the inverse Laplace transform? That's merely a Fourier transform in the imaginary direction. The Fourier transform is a unitary operator, so it preserves all the properties that it could as being a unitary operator. So that's one isomorphism. The second ingredient, or the rest of the ingredients are in Borel summation proper. So if you do an inverse Laplace transform of a divergent series in a proper Écale critical time or a proper variable so that you have exact factorial divergence, you end up with a geometrically convergent series, not an entire function, because otherwise you don't have divergence to start with in the original plane. And that you extend to the whole real line when possible, and this is the case of classical Borel summation. This process of analytic continuation is the second powerful isomorphism. As we know, analytic continuation with its permanence of relations preserves all the properties that you can imagine. So Borel summation is a combination of two comprehensive isomorphisms, and because of that, Borel summation is a faithful extension of usual summation. So it's as good as you take a convergent series and you sum it, you preserve all the properties. Okay, but life is more complicated, and often functions arising in applications do not have in Borel plane analytical intuition throughout the line that you need to take the Laplace transform, as you saw in other talks before. So then you would need to do something else, and that something else had to wait for about 100 years until Écale came with his brilliant ideas. Um, so what happens in reality? You don't have analytic continuation on the real line, but in reality, resurgent functions are functions that are analytic on a Riemann surface. In fact, you can think vaguely that they are analytic on the universal cover of the complex domain, take away a set of discrete punctures. And I'm speaking a bit tongue-in-cheek. So it's the notion of endless continuation that Ekal uses. So you have continuation, but not straight on, but on a Riemann surface. And Ekal sort of one of the other extraordinary discoveries of Ekal is that you can take an average of the analytic continuations on various Riemann sheets. That is as good as usual analytic continuation in that it commutes with all the operations, convolution included, because convolution is the inverse by inverse Laplace transform of multiplication. You want to preserve multiplication, and this procedure commutes with convolution. In cases arising in applications, the averages of Ekal are very explicit. And in the cases that we'll deal with right here, the averages are as simple as half-half because we are dealing with meromorphic functions. I don't want to give the wrong impression that taking half-half is any good in general, but if you're dealing with meromorphic functions, yes. The lines where Borel summation does not apply, and you say that things are not Borel summable, not in the classical sense, are the Stokes lines. For us, they are the most important because that's where the singularities are. And if we want to understand an analytic function deeply, we go not to a boring place where everything is convergent, but we go for singularities. So Stokes lines would play a special role. And for Q series, Stokes lines are on the other side of the boundary, meaning Q greater than 1. Okay, so this I said already about half-half. So this, because of this isomorphism, we can almost safely say the resurgent functions are equal to the Tran series. Let me put it bluntly like this. So they're, so therefore, resurgent functions in the physical domain are a superposition of purely perturbative terms, the divergent power series, and non-perturbative terms in ways of exponentials. And once more, this I mentioned before, that apart from this higher complexity, you are as good as with usual summation. Okay. The other thing that is amazing is the generalized Borel summation, a la Ekal, and Tran series applied to all functions of natural origin. This is Ekal's balance. What does it mean? I don't know. But what we know is that this is so highly corroborated that we can take that as the ultimate way to phrase it. Yeah.
Do we know any functions of unnatural origin?
Yeah. Yeah, I can create one for you. Yeah. For a small price. Okay. Okay. All right. So resurgence generalized analyticity, Tran series generalized Taylor series. So let me go to the next sort of set of slides in which we see the mock thetas and the Ramanujan-Watson-like identities as Tran series decompositions at Stokes lines. So all those complicated formulas are very simple, ultimately. Well, to do that, I have to go to the Stokes line. So let's see what is the starting point. This is one of the Mordell integrals, one of the simplest. It arises in Mach 3. Is the integral from 0 to infinity with quadratic kernels that I'm going to straighten in a moment of hyperbolic trigonometric function. As presented, if some power series would have a Borel transform this object, then it's classically Borel summable. So then we're in the boring case when you have analyticity. That's what I don't want. I want to go in a place of non-analyticity. For that, you need cosh to become cosine. In this presentation, you have to rotate S by 90 degrees, but it's better to present this integral as a bona fide Laplace transform, which merely amounts to taking S squared as a new variable. And this is a presentation of the same thing as a Borel summed series, if you want. Okay, once I have this, what do I want to do? To transform cosh into cosine, I have to take alpha all the way into negative alpha, and this is just rotation of contour. So there is absolutely nothing deep there. So you rotate the contour, either way doesn't matter, and it shouldn't, because we have to deal with some invariant kind of information over there. So I'm going to, I don't know, I put a plus minus there, you choose one, I think I ultimately chose one. So you go on the other side, let's stop short of hitting the line, and when you are close to the line, it's there that I'm going to do the proper Ekal decomposition of the integral. So this is the same Mordell integral, but on the other side of the so-called boundary. This doesn't have a boundary. And you write it as the half sum of the upper and lower analytic continuation. This is a Ekal medianization because you were dealing with a rational function, well, not rational function, with a meromorphic function. So therefore, this will be the Ekal medianization always corresponding to the purely perturbative part, and you'll have half of the sum of the residues because of this half sum business. That would be the purely non-perturbative part. And guess what? If you calculate all this stuff and what it is, you get the following relation, holding on the other side that the Mordell integral is this combination of omega of minus q and omega of minus q tilde. It's on the other side, that's why I put a v over there. Otherwise, it's exactly the Watson relation. Okay. And all these fractional powers, all these constants that are here are correct on both sides. So we are dealing with trans-series representations. The next example is Mach 10, kind of arbitrarily. Whatever we were able to check, and in the class of Mach thetas, as in the infinite list of Mach thetas that you can find, whatever we checked fits this pattern very well. And I think there is a fundamental principle behind it that we understand, so it has to be the case. So this is Mach 10. The claim being that all these relations are what? You start with one integral of your choice, as I mentioned before, say J4. You go on the other side of the boundary and you do the trans-series representation. Perturbative part and non-perturbative part. And you get all these constants by collecting residues. Okay? And this is true for all of them, but I'll claim in a moment that you only need to do this exercise for one of these because the others come for free through the action of SL2Z or SL22Z, whichever way you want to interpret things. Indeed, so what did I do here? So you have the Mordell type integrals, 8 of them here. And you want to write the action of SL2Z in this basis. And you get some matrices. These are the matrices in the usual notation in which one is the shift corresponding to SL2Z and the other one is tau into minus 1 over tau. These are the matrices. If you take ST to the power 8, you easily see, and you look at the eigenvalues, you easily see that that the action of this group, which is clearly non-commutative, it started by being non-commutative, is transitive, right? So you start with any of those integrals and you generate all of them by repeated applications of SL2Z. All in turn can be gotten by a trans-series decomposition. So it's as simple as that if you want to call it simple. The calculations, you may have to be careful with the calculations. Here is something, so Gerald was nice enough to give me this slide. So all that you saw before already somewhere. So those are Mach thetas. This is the case P equals 7 in one of the classifications. This is not Mach 7, it's Mach to be determined, maybe 14. It's an unknown case, but we can still apply this whole machinery. We get the decompositions in trans-series. You go on the other side, and as I'm going to mention in a moment, we have a numerical procedure to calculate the coefficients of the, say, generalized Mach thetas numerically out of the model integrals. And these are the first, I don't know, 10, and Gerald and his student, Griffin Adams, you now have 20 or 21 or something like this. We are yet to fit these coefficients on the usual template of a lacunary series divided by Q-Pocamer. Hopefully it's not a big deal with the 20 parameters at hand, but we haven't done that yet. Okay, so this is a new case. I mean, yeah, it is ultimately, yeah. I mean, whatever relations you have in SL to Z, they are preserved. Yeah. But the normalization is a bit different because you are working in this basis, so you have to factor out the phase. So there is some glitch like that we can discuss with. Yeah. So it's in this normalization in which you have a phase, and the phase comes from this. You have these square roots, and you have to deal with branching and blah blah blah. Okay. Yeah. No. I mean, SL to Z is the same SL to Z. Yeah. Okay. So let me sketch. I mean, this is more of an overview. I cannot go in depth in any of these things, but I'm ready to answer questions. Let me put it this way. So continuation through the boundary, that's an essential ingredient, as you saw, because you obtain these identities by sort of doing a bona fide or a non-series trans-series decomposition. So we cannot have analytic continuation through a natural boundary by definition. That's the definition of a natural boundary. But unique continuation exists way beyond the analytic continuation. There are various classical settings of unique continuation. You have Borel's monogenic functions, which are a subclass of the Kahleman-Danjois classes. And you have situations of unique continuation in analytic hyperelliptic operators. All these are functions, or classes of functions, which are not analytic, but they satisfy a number of properties, and within that class, you have uniqueness. In the Danjois-Kahleman class, if you give all the derivatives of a function at a point, those once more are not analytic functions, the function is uniquely determined. You are probably familiar with that. None of this applies here. It would be easy. So it's a different type of unique continuation, but the moral or the philosophy behind it is the same. So you have a class of functions, a class of properties that you want to preserve, and the question is whether in that class you have uniqueness on both sides. And if you do, then that's by definition your unique continuation. On the side of the trans-series, uniqueness is trivial because it's just decomposition in perturbative, non-perturbative part. On the other side is more delicate, at least with the tools that we had in that paper. Now we progressed quite a bit. But I'm going to show you how uniqueness looks like on the other side. Related to this uniqueness, or the fact that we have this uniqueness, would make it less surprising for you that we can calculate numerically the decomposition in QQ1 series starting with an integral alone, because there is a unique solution. Right? Okay, so here I wrote what we had at the time of the article. We had a complete proof only for Mach 3. It seemed to extend to other Mach thetas. Now we have a different machinery that clearly extends beyond the Mach thetas of this kind of uniqueness. However, even at that time, the fact that we could calculate the things numerically is as strong as an indication for a physicist as it may get that you must have some uniqueness. You cannot calculate some numbers if there is a wide variety of numbers that are compatible with it. Okay, so let me go briefly through this uniqueness proof. I typically don't give proofs in a talk. I think this is, at least the gist of it is simple enough that it's followable. You'll tell me at the end that I'm once more wrong and I shouldn't give any proof in a talk. So the proof is sort of exemplified on the function of omega of Ramanujan-Watson, in fact, of Watson. So these are two relations satisfied by omega, this in itself, and the second one with its partner function f, with respect to two model integrals. We retain the first identity as an identity, and from the second one, we could retain the whole of it. It's sufficient to retain a growth condition, which is what? If you look here, omega of q is related to f of q1, and an analysis of the analytic properties of this object show that as q approaches the natural boundary, omega can grow no faster than e to the pi square over 12 times the distance to the boundary, which comes from here. Bear in mind that this relation has been gotten just from a transseries decomposition on the other side. So we're not taking this from Watson. This is just from the transseries. So this relation, together with the growth condition along the boundary, as you approach the boundary, is sufficient to guarantee uniqueness. Okay, which uniqueness theorem is here. So now we're dealing with uniqueness on the mock theta side. And the claim is that there is a unique omega satisfying this relation if we impose this extra boundary condition, the growth condition as you approach the natural boundary, okay? I should comment that the growth bounds are necessary in this approach to ensure uniqueness. You have potential freedom. The potential freedom you see already, you see it in the Watson paper. There is a flurry of other functions that are mock thetas, and they are related by identities through to f and omega. All of those would fail the growth condition. And moreover, the way we analyze the problem to get this uniqueness, we identify the ultimate form of those identities. In fact, they are all those functions differ by some combination of the Haupt model of SL2 to Z. So all those ratios of thetas and Q-comers, this is one of the freedoms that you have here. This is the modular elliptic lambda function. And the theta 3 is a distraction. If you want, I'll tell you in a moment why I have a theta 3 there. Okay, and uniqueness of one is uniqueness of all. So that translates to the whole class. Let me try to go somehow through the proof. How does it go? Well, we start normally by saying if I had two solutions of what? Of a non-homogeneous equation, then evidently the difference would be a solution of the homogeneous equation. So far, so good. So omega free would be the difference of these two solutions. Okay. Next step is also something that we always do in math. You take an equation and you bring it to its simplest possible form by normalization. Namely, I want to get rid of this root pi over alpha. Well, divide by a theta 3 function and you get rid of it. I have all these distracting fractional powers. Get rid of them by raising to a sufficient power. So you do this simple exercise and you rewrite the freedom in this form here to be able to reverse this process at the end. Okay. So therefore, if I have this relation, then for some combination of this omega, I have W of Q is W of Q tilde, where W is this normalized freedom. But now what does it mean? So let me return for the moment to this e to the pi I tau and the hyperbolic plane, because that's where most of the results that we know reside. So W of Q must be a function of this tau, for sure. And this relation tells me that W is invariant under the inversion one of the generators of SL2 to Z. And this is the other generator, tau into tau plus 2, because we are dealing with functions of Q. So far, so good. So thereby, the function W of Q has to be a function of the Haupt module, because it has the same, I mean, the Haupt module, I mean, I'm speaking in a very imprecise way, but the level lines of the Haupt module cover all the possible level lines of any function living in that fundamental domain. Okay. So H is a function of lambda. I'm going to switch between the upper half plane and the disk, whichever is more convenient at any given time. In the upper half plane, lambda is the elliptic modular function lambda. In the disk is the gnome function that David was talking about. And what we know so far is a triviality that the composition between F and this lambda, which is essentially the W, is analytic in the unit disk, because W was analytic in the unit disk. But what I want to know is what this F is. And the claim is that F is an entire function, polynomially bounded. The polynomial is of low degree. You impose the growth condition and it kills it. So that's what I'm going to do in a moment. Okay, I think I wanted to say something more and I forgot, but you remind me if something is unclear. So I think I skipped something. Okay, upper half plane. In the upper half plane, lambda is a biholomorphism, wherever in the interior of the fundamental domain, right? So so this combination F composition, lambda inverse is manifestly analytic in the interior of that domain. The only question marks that we may have about analyticity are at the cusps, at the avoided values of lambda, namely 0 and 1. Okay? So I have to see what F does at 0 and 1, therefore. And for that purpose, I'm going to go to the unit disk, where this lambda is biholomorphic at 0, lambda Q being the inverse elliptic gnome. It has a Q series at 0. And in fact, it's important to have in mind that this lambda, as seen from the unit disk, is a uniformization map of a Riemann surface that can be loosely described as a cover, or maybe even more loosely. I can describe the analytic functions as being analytic at 0 on the first Riemann sheet, and otherwise you have three singularities on the Riemann sphere, 0, 1, and infinity. So that's the Riemann surface that is uniformized by this object, and that makes it easier to see the image of lambda of the disk. So excluding infinity, which is of no interest for me right now, the image of the disk is the complex domain. Take away the other avoided singularity 1. Okay, so F is analytic on this image, but it's also analytic / here at 1. So therefore F is entire. So that's the first step. And we are almost there. And now to deal with the growth conditions, you start utilizing all the identities that the modular lambda or the elliptic gnome function satisfies, and all the identities that the function F satisfies. So you have a set of equalities that you exploit to the fullest, which maybe I did it here. Yeah, I did it here when I proved the analyticity. Maybe I skipped a step, and If I haven't heard questions, maybe I already lost you here. So if okay, so I think it's safe since I haven't had. Maybe you'll ask them at the end. So all right. So the thing the way to examine growth now is to apply the other transformation of SL to Z, tau into tau plus 1, which transforms Q into negative Q. Lambda becomes 1 minus 1 over lambda. In the unit disk, lambda at 0 behaves like Q. So this one behaves like 1 over Q. And if I plug it in, I have f of 1 over Q, essentially. And it's easy to see that this combination covers a neighborhood of the North Pole on the Riemann sphere. So I have a grip on all the values of f if I have an overall bound for f, which I do from the bound that I had on omega. You remember that blah, blah, blah. Omega is bounded by this. You translate that into whatever it means for the cured omega, which was the 6th power divided by theta and so on. And this translates into quadratic bounds. So now I have an entire function which is bounded by a polynomial of degree 2, so therefore it's a polynomial of degree 2. And then you start an easy game. You start dismantling the transformations that got you there in the first place. It turns out that square root of f must also be a polynomial, but it's 0 at 0, so the constant part here must be 0. But at 0 is quadratic, whereas this itself is linear, which is a contradiction unless they say is 0, so f is 0, and you're done. So that's the gist of it, and as you see, it does employ the growth condition, and it does employ the modular transformations. Okay, and yeah, I'm near the end. So you, with the Mordell integrals and resurgence, you can analyze any kind of the behavior at any kind of boundary point, or I should say rational point on the unit circle where things exist, and in this case, these are all of them. And that's basically a trivial exercise in resurgence analysis and rotation of Cantor and transformations. And I'm just going to skip this. So this resurgent analysis gives you access to other points. And I'm going to say a couple of words about the numerical procedure and maybe stop there. So we have growth bounds as you approach the unit circle. Those bounds are gotten for free from the transient decomposition on the difficult side. Those translate into bounds in the growth of the coefficients. And if one can obtain quite sharp bounds by elementary means, namely asymptotic analysis of Cauchy-Cantor integrals. So in both directions. So you take you write the coefficients by the Cauchy formula, and then you see the saddle points of that problem. You do a saddle point analysis, and you get asymptotics of coefficients, and essentially you can go vice versa. This is crucial in the numerical procedure that does what? So let me assume that what I want to calculate is this omega, and I don't know it, I pretend. So I start with the identity that omega satisfied, and I wrote it a number of times. Omega of minus q plus omega of minus q tilde plus times something equals w. But I don't know the coefficients of omega, pretend, so I take them as unknowns. So I take a series for omega of minus q plus root of pi over alpha omega of minus q tilde with unknown coefficients. I go to the softest possible place of analysis, that where q equals q tilde, which is e to the minus pi. And you take this expression and you expand it in Taylor series by that point, and you take the Mordell integral, you expand it in Taylor series by that point, you get what? You get a system of algebraic equations. You truncate it somewhere and you solve it. It's easy to show that at this finite level, you always get a solution. The matrix is always invertible by completely, for completely trivial reasons. Does that solution have anything to do with the coefficients of omega? That depends on whether the when the truncation order goes to infinity, I converge to something. And that's where we get into deeper things. There are some very interesting things that happen. I can say in a word that this, whenever you have uniqueness, this works. And I'll return to this in a second. So this is a numerical calculation. I just kind of arbitrarily took a system 100 by 100. And you get the coefficients of these supposedly unknown function omega. The first one is within 10 to the minus 22, it's 1. So if a physicist, you're not convinced that that is 1, you're becoming a mathematician as I became. Okay. And you get up to 27, 28, whatever, with very high accuracy. And if you refine a bit the system, you get 100 coefficients out of it.
At intermediate stages, before you take this limit, you always had algebraic numbers, did you?
I do what?
The numbers which gave you these things for the nearest integer, in your calculations, were they always algebraic numbers?
No, they aren't. They must be transcendental, because where do I get them from? I get them by expanding q, which is e to the minus alpha t, but e to the minus pi square over alpha at that midpoint. And those are transcendental. Okay. Okay. And that's, so that's the numerical procedure that was refined by Gerald and his student to get 20 coefficients of the unknown case. And it works. I mean, we tested it for Mach 10 for all the Machs. So it's a convergent procedure. There is some theory behind it, so I can prove convergence in some simple cases. The amazing thing is the following, though. That is maybe only partly understood. So as I said, the finite dimensional system always has a solution. Now the question is that of a limit. So you look at the lowest eigenvalue of the finite matrix. The infinite dimensional object, which is necessarily a compact operator because it's a limit of operators of finite rank, is guaranteed to have an infinite dimensional kernel. And the kernel consists of all those combinations of the Haupt module. So far, so good. What is amazing here is that what generates those functions of the Haupt module is something completely elementary. So the ingredients here to get that kernel are simply Taylor series expansions of e to the minus t and e to the minus pi square over t at e to the minus pi. You do that, and it's a Haupt module generator for a large class of things. So I played in obtaining the Haupt module for SL2Z / gamma 3, gamma 6, gamma, and you get them in this completely elementary way, numerically though, but very convincingly. I'll just stop here. I'm already over time, and thank you very much.
Theorem, you had a growth condition, omega q to the 1/12. What happens when that's tight?
What happens when you are on the margin of it? Yes. We have no example of such a thing because the gap in practice is typically huge. So let me go back there. Let me see where. Yeah. So my guess is that the convergence would be so poor that it's useless.
My intuition is that it's also very interesting. You're saying it's...
No. I mean, that doesn't mean it's not interesting. I'm just saying that numerically it wouldn't be a good procedure. Yeah. I don't know. It goes by orders of magnitudes faster as you approach the boundary than omega itself. Yeah. To generate the. Yeah, yeah. I mean, that's, I think, essentially what Gerald is doing. It's more complicated, but it follows from this trans-series decomposition on the other side. It gives more. Yeah. So this is already, insofar as we know, is not known, whatever expression that is. I don't know if this is too small. So this is P equals 7. This is not Mach 7. P equals 7. If you look at the model integral. So I don't think this is one of the known cases, or is it? A higher depth is. Double integrals. Well, maybe we can discuss, because typically we have ways to bring higher dimension integrals into one. So by retaining the resurgent kernel and integrating overall the other variables. But I have to see how it really looks.
Do those
Sorry.
numbers conjecturally count for something? I mean, they're constant sign increasing monotopic theory. Do they enumerate something?
They should. I mean, why else would they be integers? But this is not a good answer. And the good answer, the honest answer, is we don't know what those numbers are yet. The expansion, I mean, the coefficients are integers. Why transcendental? No. So David asked whether. So what I said is kind of. I mean, at least it amazes me. The following thing. So the lowest eigenvalue of the compact operator that you get from these finite dimensional matrices gives you the Haupt model of whatever you want of your choice if you go in higher order Mach thetas and so on. Whereas the source of that information is in the Taylor series expansion of Q and Q tilde, just that. Meaning e to the minus t and e to the minus pi square over t. There is some magic of taking some limit of that, and you get the Haupt models of SL to Z factored by you name it. And David asked whether these numbers, which are the Taylor series coefficients, are rational numbers. Half of them are from e to the minus t, and half aren't from e to the minus pi square over t, or something like that. Or neither, because it's the expansion at t to the minus pi. Maybe neither. None of them are, rational. Transcendental. Yeah. But does the circle method give you the coefficients in, I mean, can you calculate them exactly as integers? From the asymptotics, I don't think you can get very far, because the asymptotic, from the asymptotics of the coefficients. That's a good point, but is it the asymptotics of the coefficients that you obtain from the integral or from the Q series? Because it's a different animal. And I think you get them from the Q series, and then it's not unexpected. I mean, you have asymptotics essentially to all orders of something that comes from the Q series, but I don't have the Q series. I have the integral. Can I use the asymptotics to calculate those, or can I use the integral to calculate the asymptotics without being given the Q series? So I return the question in this way. So I think this is the difficult part.